I think, I guess,
Yeah, we can
now it's
start.
8
Yeah.
o'clock.
Purvita?
Yeah. Good evening, everyone. It is my great pleasure to introduce Professor R. Ramanujam in our webinar. He is currently affiliated with the Institute of Mathematical Sciences, Chennai, and is interested in the applications of automata theory, mathematical logic, and philosophical logic to problems in theoretical computer science. This has led to research in theory of distributed systems, interaction in multi-agent systems, game theory, and security theory. Today, he will give a talk on decidable fragments of first order modal logic. I hope all of you will enjoy the talk thoroughly and ask questions. Jam, it's over to you. Please continue.
Thank you. Thank you very much. One moment, I'll do share screen. Yeah. I'll do, yeah, once I do full screen, I'll have to come back, stop share, and go again, because for some reason, otherwise the slides don't move. Okay, now I hope it will move. You can see, right? Okay, so let me start with a salute, as I said, and thanks to Purvita and Amit for organizing this seminar series. I can't really thank them for the invitation to talk because I invited myself, but well, one should. I mean, I think this is our seminar series and we should own it in that spirit. So I'm very happy with that. And I think this is perhaps one of the best logic seminars. It has been my pleasure to attend. I've really learned a lot over the last few months and hope I will learn more as we go along. So thanks very much for doing this wonderful work. And like Purvita said, please do not wait until the end to ask questions. Interruptions are welcome. And I see that Ananta Padmanabha is in the group. So it's excellent because he could give this talk. He should, in fact, give this talk. So, and I'm doing it only because he's not doing so. And so, yeah, a lot of the work that I'm going to talk about also is his and other people's. It'll be, yeah, so I can always deflect things to Ananta if it gets heavy. Okay. Yeah, so here is the summary of the talk. It's going to go in a couple of slides. Well, the news from 1936 was that first order logic is undecidable. And that started off a lot of work. Actually, by the time Turing proved the undecidability of first order logic, people had already been working on different fragments of first order logic and showing them to be decidable. And one of the most beautiful results was by Ramsey, who showed that there exists for all fragment is decidable. And in fact, one of the lemmas in proving that fragment decidable was what we call the famous Ramsey's theorem now on partitions. It has led to the whole field of Ramsey theory. So it's not, this is yet another of those instances where work on a fundamental problem in logic led to areas of mathematics. So, and Carnap, various people had been working on different fragments. And Lowenheim's column, one of the early results. So when Turing came along and showed that first order logic is undecidable, and then Tarski posed several problems formally, and then what we call the classical decision problem took shape. There is a typo there. Identify the decidable syntactic fragments of first order logic, right? Find the borderline between decidability and undecidability. And I would call this one of the most successful projects of the 20th century. It took 50 years. By the time all the things were mapped out, for different vocabularies, like syntactic restrictions for quantifier prefix classes, with restrictions on vocabulary on number of variables, use of function symbols, scope of quantifiers, and all of these were fixed. It was really the 1980s. Some great, efforts were made. For instance, the role of equality. Some logics in these fragments are decidable with equality. decidable without equality, but not with equals. In, it's a tale I love to tell because it was a mistake of Gödel. One of these fragments, there exists star for all star, there exists star. And Gödel gave a nice argument and then said that in the footnote that this sort of thing can be extended with equality. And that set back research by quite some time because many people couldn't prove it. Eventually, Goldfarb in 1981 or something like that showed that it was actually undecidable. So even Gödel was wrong, which is very reassuring for mortals like us, right? I mean, but it's also important, therefore, to try so many things. Yeah. And then semantic restrictions, constraints on models by fixing interpretation of predicates, desirability of theories of order, arithmetical theories. I mean, very early on, Tarski showed the desirability of real arithmetic, but the complexity of real arithmetic was settled as late as 1990s. Uh, you know, Ferrante and Rokoff gave triple exponential bounds, but the actual borderline was fixed only in 1990s. Algebraic theories very, very early on, theory of algebraically closed fields, Abraham Robinson's work. And then that's something that has really moved phenomenally. Combinatorial theories, theories of on first order theories of words, uh, trees, different classes of graphs, and that's a flourishing cottage industry even now. And then once we find decidable fragments, we seek to extend them with constructs which are not F4 definable, like first order logic with transitive closure. Transitive closure is not first order definable, and you look at and now, can I get decidability now? Where can we get decidability? How far can I push? Set quantification, monadic second order logics, fixed point extensions, and some of these are not decidable. You know, what exactly is decidable when is a very interesting question. And like I said, I call this still a project of the 20th century because bulk of the major work was done from 1930s to end of the century. Still, many questions are being worked on, but you know, uh, it's a good tale to tell. The book, The Classical Decision Problem, is a very good place to look at all the results. It's like a one semester course to learn these different fragments and understand the tools and techniques involved. On the other hand, yeah, propositional modal logics have been extensively used in computer science. I think since the 1980s, late 70s, logics of programs people started working on. Von Pratt defined dynamic logic. Tony Hoare defined Hoare logic, and Salvitsky was looking at algorithmic logics. So, and people quickly realized that propositional modal logics are very attractive for these. And a lot of work got done in the 80s and 90s. Many extensions of modal logics are decidable. Vardi wrote a very nice paper, and gave a very good talk in 1996, where he asked, why are modal logics so robustly decidable? And in the sense that, first order logic, you try to add anything, undecidability is waiting for you. Even if you take a decidable fragment and add just a little bit, it becomes undecidable. Whereas modal logic is decidable, but also robustly decidable in the sense you add all sorts of stuff to it, it remains decidable. Dynamic logic is one very good example where you're adding transitive closure or a fixed point inside the two variable fragment of first order logic, which is decidable. But then it turned out that that's not quite correct because many extensions, fixed point extensions, for instance, which modal logic preserves decidability with, but doesn't work with two variable fragments. And then Andreka, Van Bentham, and Nemetis suggested that no, modal logic sit inside the guarded fragment of first order, where formulas are guarded. So I'm not sure. We'll see that later, but yeah. I'll talk about this a few times. And probably, I think there is increasing evidence to suggest that maybe that's a good answer to that. But so these are two stories. One on decidable fragments of first order logic, and the other is with modal logic. But what happens when you try to combine the two? And
Jam, can you please explain what is guarded fragment?
okay, yeah, guarded fragment. Wait a minute. Yeah, guarded fragment is if you translate first order logic into, I'm sorry, if you translate modal logic into first order logic, the modality, I usually call it box, okay, necessary alpha, translate to for all x, right? If I see a y, rxy implies alpha of y, right? So the modal formula alpha is being guarded by an atomic formula. It is of the form for all x.
Okay.
An atomic formula implies something. Or dually, you will say there exists x, some atomic formula and the translated formula, right? So the guarded fragment of first order logic is one where you, every time, so it's not that you control number of variables or anything, but if you take a universal quantifier, you write it of the form for all x, some atomic formula implies, and then recursively the other. And then similarly, your existential formula as there exists x, some atomic formula, and something. So these atomic formulas act as guards, protecting you from what's coming, right? So, and then the free variables, so if I write an atomic formula of the form Rxy, to the right, that implies a formula whose free variables are x and y. You can have further existential variables coming. So that's about all. So Rxy says your x and y are free, right? You're going to work with them, but they better be related by this. So that's the guard that you're going to
Okay.
So that's the translation, natural translation. And they look at the guarded fragment and show that to be decidable. And that guarded fragment is also robustly decidable in the sense that you can take fixed point extensions of guarded first order logic, and they are decidable as well. And that's a very, very nice result. Eric Gradle and some others. I don't remember the authors. Some others. Yeah. Anything else?
Thanks a lot for the answer.
Okay.
Yeah.
Now the sad tale is that you try to combine the two, everything is bad. In 1962, Kripke wrote a very nice paper where he showed that first order modal logic is undecidable. So you take first order logic and modal logic and combine the two. Very natural thing to do. And in fact, modal logic, when it began and in its journey in the early 20th century, more than 100 years ago, and people were actually interested in first order modal logic. That's how it came. And because first order logic, well, we'll see. Yeah, first order. And so Kripke showed that even with a single monadic predicate, just with one unary predicate, and no equality, constants, function symbols, the logic is undecidable. So it's notoriously undecidable. In 1978, Fisher survey in a paper, and then Segerberg showed that one variable fragment is decidable, but one variable fragment is so weak. Huh? So pretty much all attempts, and you will see more of the sad tale, right? So whatever you try to do, the logic remains undecidable. So it seemed pretty hopeless. But in the last few years, this is really 21st century research, right? Okay, because that I said was 20th century. Now we are talking about 21st century because the earliest results of this kind date back to 2001. So, and mostly it's in the last maybe 10 years or so, or last 4 or 5 years, really. Yeah. So the monodic fragment is shown to be decidable. Some what we call bundled fragments, some fragments of term modal logic. Again, you will see the guarded fragment, two variable fragment, they're all decidable. Now, the good news in saying this is that these results indicate that there is plenty out there for those who care to take. Okay, it's not just the results. In the sense that these logics are decidable is interesting to me, but in terms of mapping the terrain, if you start looking at, what kind of possibilities there might be, like I said about the decision problem, right? Or first order logic. If you start thinking now, what fragments of first order modal logic might be decidable in terms of model classes, in terms of different kinds of interpretations that you can give, in terms of syntactic conditions. The good news for me is that there is a lot out there that we don't know, right? I would say also proceed with caution, because, for instance, there are situations where we can show that addition of a couple of constants can make the difference between decidability and undecidability. So it's subtle, but it's all the more inviting because the terrain is definitely not mapped, right? There's a large dark area out there that we don't really understand. For instance, some of the research that very, very recent research that tells me that with equality, we are back in the days of, dark ages of 1940s and 1970s, right? Where, like I said, theories with equality and theories without equality, and people struggling with these, some of them being decidable, some of them being undecidable. I see something like that happening with these logics as well. So all this to say that there is something very interesting going on. We have no idea. Maybe it's all easy stuff, but I don't know. But what is very interesting is that the results, more than the results, the proof ideas being fairly elementary model theoretic approaches suggest that there is, more out there for us to dig. Yeah. So that's really what I want to say. So this is really the summary of the talk. So time for people to go to sleep. Yeah. And now you can tune. Yeah. So first order modal logic, as I said, well, it's a theater in which numerous philosophical controversies have been played out. Big debate between Quine and many other logicians. Quine really hated first order modal logic passionately, and I'm not particularly in this talk. I'm not going to talk about the controversies and the difficulties, but just to say that there is a lot of technical difficulty as well, and I'm only talking about this whole thing from a viewpoint of decidability, and that's a very limited viewpoint. But first order modal logic is very interesting from a conceptual abstract sense as well. For instance, when we write first order logic, we write sentences like, for all x, there exists y, such that x is less than y, x is sitting. Okay, it's a good first order sentence. And in computer science, we write sentences like all processes are terminated. Now, this is true in some states, this is false in some states. So this is what you call a contingent proposition, right? But it's a stable proposition, because once it may not be true, but once it becomes true, it's true forever, right? No amount of state changes will change anything, because everything is terminated, so nothing can come alive, right? So, and then you have statements like every request is eventually granted. This is another thing that computer scientists like. This is a modal proposition. It's modal because something that is true, right? A request is true now. I got a request now, right?
Right.
And I'm,
And I'm
yeah, I got a request now, and I'm not granting it now, right? I've got 10 requests now. I grant one now, grant one later, and so on. But I'm making sure that every request is eventually granted, right? So this is a modal proposition, and you can interpret it as in a temporal terms, right? In future, sometime in the future, it is granted, or there is a reachable state where you will find that all the requests that were made have been granted by them, right? And you can give semantics to all these things. And the second and the third are typical sentences in modal logic, propositional modal logic. Then you have sentences like these.
May I ask something?
Oh, yes.
Hi. So,
Okay.
did you use stable in any formal sense, or just as you explained.
Yeah.
Stable
Oh,
preposition.
yeah. I mean, it can be formalized very nicely also. But of course, I mean it only in the sense that something is terminated implies box terminated. Yeah.
Okay.
And that's valid. I mean,
Thanks.
in the meaning of processes and termination, yes, it's valid.
Okay, thanks.
But yeah, it has nice mathematical meanings. That okay. But Moa, you had something more to suggest on that?
No. I just wanted to clarify. That's all.
Okay. Yeah.
Thanks.
Now, and then there are sentences like this. Every currently dominated element can become the dominator. You know, in these days of elections and so on, it's the kind of sentences that you want, right? Now, it says you take any element, currently it's dominated by Y, then maybe after an update, after something happens, temporarily or by some action, whatever, there is a future or there is a new state where this becomes the dominating element, right? In fact, it dominates every other element. So, and notice that this X is standing across the two propositions, right? X is free here. X is a variable that gets an interpretation as an element now. And we are talking about that element from this state to the next state, right? To whichever is the next state that we are talking about. It is the same element that is being bound across different different worlds. As you know, in modal logic, you give the semantics of modal logics as sets of worlds. And when you use term like diamond alpha to say that I can see a world where alpha holds. But then in first order modal logic, there is this extra complication because I am quantifying across worlds. There is quantifying within a world, but there is quantifying across worlds. And it turns out that this is a really important thing to think about and worry about, at least from a, as I said, there are philosophical reasons why you worry about this as well, but there are also, you know, decision procedure, like algorithmic reasons to worry about this as well. Okay, so propositional modal logic. Now this is something probably everybody knows here, I don't know, but it's, you know, quickly, what is that? You take propositional logic and extend it with a unary operator. And box alpha is read as alpha holds necessarily, and its dual diamond alpha, which says it is not the case that alpha holds necessarily, which you read as alpha holds possibly. And its semantics is given as possible words, also called cryptic structures. It's a possible word semantics is used cryptically. So you have models are triples, you have a set of words, a binary relation, which is usually called the accessibility relation, and then you have evaluation, which assigns to every world, which are all the atomic propositions that are true in that world. So if you take world W, if P belongs to the of W, you interpret it as proposition is true in that world. And the idea is that in general, so obviously because of this valuation being like this, it's, you know, a proposition may be true at one world and false in another world. So that's how you say it's true now, it becomes false later, etc. You remember that element being something and becoming something, being and becoming very simple. And so you say proposition P is true at a world if P is in the valuation of that world, and alpha necessarily holds at a world if in all accessible worlds alpha holds. And it's easily seen that it's dual. Diamond alpha holds at a world if there is a successor or there is an accessible world where alpha holds. And alpha is satisfiable if there exists a model and a particular world W where alpha holds. And it's got very good properties. It's got good model theoretic and algorithmic properties. It's a fragment of first order logic, like I just mentioned. As you can see, you can translate You basically start with atomic propositions, interpret them as unary predicates, and then you build the translation. Diamond alpha gets translated as there exists a y such that there is an edge from x to y, right? That binary accessibility relation is a binary relation. And then you have the translation of alpha. And box alpha is interpreted as for all y, if there is an edge from x to y, at y, alpha holds. Yeah. So this is the first order formula. So you have a fixed binary relation here, and you have unary predicates talking about propositions, and then you have translated into law. In fact, what you can show is that, so it maps it into the two variable fragment of the logic. That's also nice to observe. And it is mapping into the guarded fragment of first order logic. And this is really the definition of the guarded, the idea of a guard that I just talked about. And satisfiability is p-space complete. Well, who cares about p-space? But it's, it's decidable as far as we are concerned. Model checking is linear in the input. That is, if k is the size of the model, k is the model, and alpha is your formula, it's linear in here. So these are good properties to have. Now, modal logic is very weak in terms of expressive power. There is no equality, right? Instead of instead of box alpha, I could have actually indexed it, right? Instead of one accessibility relation, I could have finitely many accessibility relations and index them saying 1, 2, or A, B, etc. Right? So I can talk about after every A successor, alpha holds, or there is an A successor where alpha holds. But then there's no way I can force the two successors to be equal, right? I cannot say that from the current world or a current state, both an A transition and a B transition lead to the same state. Now, and this is something that you might want to say, right? No matter what A and B I do, I'm always going to land up in the same state. They both have the same effect. You can't say such thing. Bounded quantification, in the sense that we cannot say that a property holds in all states, right? If you have a formula has some modal depth k. So sitting at a world, I can talk about paths of length k by saying diamond of P1 and diamond of P2 and so on. I can build paths, but I can only look at boundedly many states sitting at any place. I can't say far away somewhere. And then you can't define new transitions, right? I mean, for instance, we have this edge relation EXY, right? Suppose, there is an A indexed relation and a B indexed relation. I want to say both, right? I want to define a new relation. You can't define something like that. So propositional modal logic is very nice, but, there is some limitation of expressiveness. More on the list of complaints, no counting. You can't say there is at most one A transition system A transition from the current state. Now, for specification of systems, this is very important because you cannot force deterministic systems. I mean, you can't distinguish deterministic systems from non-deterministic systems. In general, your formulas specify non-deterministic systems, and you have to, if you want to do some determinacy or determinization, there is some work involved. And in the 80s, Joe Halpern and co-authors did a lot of very interesting work on doing some of these things in the context of dynamic logics. But in general, those are, if you just want to distinguish between one and many, it's possible. But if you want to count, well, then it's a problem. But then you can look at counting extensions, and that's what I'm saying. And the other is no recursion. We can only look at a bounded number of transition steps that I said, but that's a limitation shared by first order logic as well, right? In the sense that there is this very nice locality principle that first order logic has, and you can take wherever you are, and there is a bounded sphere that you can impose and say that all your witnesses are always to be found within a certain radius, if you like. So that's a very nice Geitman locality theorem, which first order logic has, and it's actually very useful. So, but then modal logic is still very interesting on many counts. As I said, it has very interesting model theoretic properties. You can show that formulas are preserved under bisimulation. Now, if like the notion of isomorphism, elementary equivalence, what is elementary equivalence for modal logic? Well, here, at least for finitely branching systems, elementary equivalence corresponds to bisimulation. And that's a very nice theorem. Bisimulation is to say that if you have two non-deterministic systems in general, or two cryptic structures here, whenever I can do an A here, I can do an A there and match. This is it. I'm not going to do much into bisimulations. It's just to say that that's a very nice characterization you have. And Van Bentham's beautiful theorem shows that modal logic is in fact the bisimulation invariant fragment of first order logic. Like we provided a translation from modal logic into first order logic. You start with first order logic of the appropriate kind and ask which are the formulas that preserve bisimulation. That's exactly the modal logic. That is, you can do a reverse translation and get modal formulas. It's got the finite model property. It's got the tree model property. So given any formula, you can show that the models have very nice structure, so you can manipulate. So all this is there. And so numerous extensions to overcome the limitations that I mentioned have good model theoretic and algorithmic properties. You can add transitive closure. You can add temporal operators on paths, linear time temporal logic. You can add temporal operators on paths as well as quantify over paths. And then you have new calculus, which is a fixed point extension. And it naturally gives you fragments like game logics, description logics. So, and all of these have very nice algorithmic properties and model theoretic properties. So the mu calculus, for instance, you can show satisfiability is exponential time complete. Model checking, in fact, in general is an NP intersect co-NP. And one of the very, very nice open problems of the subject is to ask, is there a polynomial time model checking algorithm? That's open. And you can show that it is in fact the bisimulation invariant fragment of monadic second order, which is by Janine and Valukiewicz, a very nice model theoretic result. So that's why Vardi asked this question. And as I said, standard translation does not do more than 2 free variables. And is that a good explanation? And so this was actually quite some work was done on this. And in general, 2 variable logic, I'm mentioning it because we'll see that later again. So if you have, if you consider the relational fragment of first order logic, right? That is no constant symbols, function symbols only, no constant symbols, yeah, no function symbols, and you have only k free variables, right? And k variables. So for instance, here is a, yeah, there exists a path of length 70. That's in the 2 variable logic. Because I can reuse variables, right? This is the important thing. I say there exists x, there exists y. There is an edge from x to y. And then there is an x such that y, yeah, it should have, but yeah, should have stepped through, yeah. So I can go from x to y, y to z, you know, that's really what I want to say, right? x0 to x1, x1 to x2, x2 to x3. But as I go along, for alternate quantifiers, existential quantifiers, I can keep reusing the variables. So in general, but then you can show that even for 3-variable fragment, the satisfiability problem is undecidable. And it's true even with a lot of prefix classes. But 2-variable fragment is interesting. Scott in 1962 showed that without equality, it can be reduced to the Gödel class. Basically, it's decidable. Very, very nice normal form exists for this logic, and you can use that for manipulation. And Mortimer showed that it has a finite model property. And then by 1997, its complexity was fixed, and that is 6p time complete. But then it's not nearly as robustly, as I said, modal logic sits inside 2-variable first-order logic, and modal logic is robustly decidable. So this was one explanation, but as I said, the answer was that it was not, because it lacks the tree model property, that one of the. So for instance, consider the formula for all x for all y exy, right? It says that if E is the edge relation, it's completely connected, right? And so you can do a lot of coding of grids, which is one very standard way of obtaining undecidability. So with many extensions, it turns out to be undecidable. And it's not only the use of 2-variable logic, but also this guarded fragments. So quantifiers can always be relativized by atoms. And in the modal fragment of first-order logic, each subformula can speak only about elements that are closely together or guarded. This is the term introduced by Andreka, van Bentham, and Nemeth. And this is the guarded fragment that I mentioned earlier, and Amit was asking. So quantification is always of this form where alpha is atomic, and it contains all the free variables of phi, right? So the only free variables that you can have here are x and y. Of course, you can have lots of bound variables, and as I said, that actually lets you go quite far. But so these kind of syntactic fragments are very interesting and important when we get to modal logics as well, first order modal logics. Yeah. So in fact, they gave a challenge, right? The guarded nature of quantification in modal logics is the real reason for their good algorithmic and monodic properties, and results since then show that they're probably right. I mean, of course, I don't think I can prove this as a theorem.
Jem, we can't hear you. No, we can't hear you now. Yeah. No, not yet.
Yeah, what about now?
Yeah. We can hear it. Yeah.
I think there is some loose contact somewhere.
Yeah.
Yeah, so all this wisdom suggests similar approaches to first order modal logic. You know, like management people say, right? Combine the best practices of these elegances of humor. So, but unfortunately, FOML seems to combine the worst of the two, even in its simplest versions. And that's something that you should always be prepared for, right? You take two good things and put them together, right? The worst of both come together. And oops, yeah, so first order logic, I think everybody knows exactly what is first order logic. But just to say that, I'm going to limit myself to a vocabulary with no function symbols. So only relation symbols and constants. So terms are just variables and constants. So when you say first order logic, we are only having this in mind. You have atomic formulas, you have equality, negation, disjunction, and quantifiers. And semantics, of course, is given by a first order structure where you have interpretations for constant symbols as elements of the domain. And you have interpretations for every predicate symbol. It maps it into a set of M2s. Every predicate symbol of proprietary is mapped quickly. And then you have a variable, an assignment of variables to elements of the domain, which you lift to terms and then interpret your atomic formulas in the model by saying, well, evaluate the M tuple of terms. That's an M tuple in the domain. apply the interpretation for the predicate symbol. If that is 1, that's when it is. It's a one-slide introduction to this terminology. And for all x alpha holds in the model, if you take all domain elements and if you look at the model variant, where x gets the value d alpha. So this is to tell you that when we talk about first order modal logic, the first order part that we are talking about is the good old first order logic. It's not that you are messing around with the meaning of quantifiers, you are messing around with the meaning of connectors. So whatever jugglery we do is preserving this. So that's about all. Nothing more to say on this. So what is first order modal logic? Well, it's a natural combination of first order and modal logic. One thing I've done is to throw away the function symbols, but apart from that, you have constants and variables, you have terms, you have atomic formulas, you have equality, negation, disjunction for all x alpha and box alpha. But the semantics is more complicated now. Why? Well, for propositional modal logic, what is our semantics? We have a bunch of words and an accessibility relation. And the words interpret propositions because it's a propositional logic. But now you have first order logic sitting there. So at every word, you need a first order structure, right? So every word we need to associate a first order structure and interpret terms as elements of that structure, right? And but then, as I said, you need to have a print statutory warning. This can get quite clear. Because how do you relate? This is the point of coherence, right? If two worlds are W prime is accessible from W, how is the structure at W related to the structure at W prime? Right? If I have a variable X mapping to a domain element D at W, what is it going to map to in W prime? Maybe it's a completely different domain, right? And so those elements may not exist. Yeah. So the existence problem is quite non-trivial. And this is what led to all those philosophical debates that I was mentioning. Right? And so just giving semantics is painful. So interpretations as well as variables, assignments need some coherence across words. Well, one question to ask is, why is it reasonable to fix a single domain for the entire universe of possibilities? If you say set of words, you might as well call it universe. And say that I'm going to, this entire tricky structure or whatever structure that you come up with, right? So you have a single domain and all reference to elements when you're quantifying anywhere are ranging over that. This is one natural, and as I said, but I'm asking it as a question because, as I said, many philosophers are questioning this. So the constant domain interpretation, this is what I just said, there is a single constant domain over all words, as opposed to varying domain interpretations. But the main, and then you can do that, but then you have to say that when you take the varying domain interpretation, all quantifications are over the current domain. Wherever you are, like you are interpreting your formula at some world, right? That world has a domain. So when I say for all x, I'm going to interpret as for all x over that world. So it's going to be like for all x alpha, and then diamond for all x alpha. Right? The first for all x alpha interpreted at W may have a particular meaning. And then you move over to the new word, the for all x alpha has a completely different meaning. Right? And this is the kind of mess that you have to deal with. So, and oops. Now, question is, how do you interpret even something like box, PX or not PX? I mean, this is the mildest thing you can think of, right? It's a tautology, right? No matter what I do, I box true. Huh? This is something you want. But X is free, right? Now, suppose X evaluates to D in the current world, but D does not exist in the some accessible world. So your formula is meaningless. It's not about being true or false, right? PX or not PX, where X evaluates to D, has no meaning at all in But then you can't say that I have a free variable which I evaluate to something, but then I go to another world and then I lose the valuation. Okay. So one solution is to impose a monotonicity condition. That is, says if D exists at W and W prime is accessible from D, W, then D exists at W prime. Right? So this is normally called an expanding domain. Basically, you have a domain at W, and as you go in reachable worlds, your domain keeps expanding. You never throw out anything. No element dies. Right? I mean, this is just one way. Huh? As I said, if you look at the literature on first-order modal logic, and Mel Fitting has a very, very nice book on first-order modal logic. It's an old book where you can see lots of interpretations and statements. And then there is this idea of rigid designator. It says a free variable is interpreted uniformly across worlds as opposed to modally varying designators. I mean, it can be really crazy if you start doing this. Okay, this is only to say that if you want, you can get crazy. We don't have to worry about that because, as I said, this thing is so notoriously undecidable. You don't need craziness. Even the very disciplined part is undecidable. So, but this is if you want to work in the positive direction, there's a lot of craziness awaiting you to explore and enjoy. So the simplest semantics is the constant domain interpretation, right? You have a bunch of worlds, but there is a single domain, right? A constant domain, such that your interpretation of constant symbols is independent of the world. And this is very important, right? An element, if you have a name in your logic, that name, if it gets interpreted differently at different worlds, right? So if this, in general, this interpretation of a constant symbol could be dependent on the world. Right? And this, as I said, is fertile ground for philosophers to. Oh, I'm sorry, there is some backslash missing here. Okay. This is an assignment. So this is, again, the rigid designator. If you have a variable, free variable in particular, that maps to a domain element independent of which word. So that's why it's rigid. And there, of course, the interpretation of predicates varies. Right? The relationships vary in different worlds. And every world, the relationship between elements is different, but the domain itself is constant. And that's very simple to give semantics. Well, you can ask, is the formula for all x box alpha implies box for all x alpha? This is called the Barkan formula. And with this, you can see that it's valid. See how it works. Well, what does the assumption say? No matter what element I choose, wherever I go, alpha goes. Right? And remember, it's a constant fixed interpretation. So no matter where you go, I mean, you look at it as in terms of suppose not, right? Suppose it's not valid. You have a model where the premise is true, but the conclusion is false. That means I have an accessible world and a variant where alpha goes. Now you can go back and construct a variant of the original world and show that that formula would have for all examples. So it's a. What about the converse Barkan formula? Is it valid? Well, I leave you to enjoy figuring out. Here is a formula. For all x box, there exists y, x equals y is valid. Well, because I have a constant interpretation. And this is a formula that really, it seems like something pathetic to say, right? If you have any x, no matter where you go, I'm not even saying not equals, equals. Right? This just says that if an element exists, it will continue to exist wherever. Okay. Now, okay. Let's get to it. Sorry, I've already taken too long talking about this stuff. Undecidability. Consider first-order logic with a single binary predicate. Okay? And this was already shown to be undecidable by Vardi. And in 1962, Kripke reduces the problem to satisfiability of first-order modal logic formulas with unary. And the coding is ridiculously simple. you take this one binary predicate and interpret it as, take two unary predicates, and the relation between x and y is now in that domain, is given by, I can see a world where some px and ry, new predicates, new monadic predicates. And then you lift. Now you can show that the original formula is satisfiable if and only if the translated formula is FOML satisfied. And the proof is completely straightforward. If you see what you are saying is that if you had, the whatever interpretations you have got for your predicate symbol are maintained consistent, and the idea of diamond being different possible verbs, right, across the leaves, tying up together is something that the formula is doing with the quantification. Correct. It's a very simple proof and it's very robust. And you see that it brings it all to formulas of modal depth. In fact, so the tale of woe, Walter and Zakharyachev, yeah, they lament the monadic fragment of practically all predicate modal logics. In first order logic, if you restrict yourself to the monadic fragment, that is unary predicates only, right? That was shown to be decidable by Lovenheim in 1913. And whereas if you take, like we have just seen, the monadic fragment is already undecidable. In fact, the two-variable fragment of practically all predicate modal logics is undecidable, even with constant domain interpretation, without equality, without constants. The coding is also very simple. Basically, it leaves only the inexpressive one-variable fragment. But then they go on to study what they call the monodic fragment. And the monodic fragment has been studied in other contexts. There is a quotation from their paper, it's quite nice. All undecidability proofs of modal logic, its formulas in the form, it's a two-variable. It's not copied correctly. The main thing is the necessity operator, the box formula, applies to subformulas of more than one field. And in fact, such formulas play an essential role in the reduction of undecidable problems. Like for instance, you saw QXY was translated to diamond, PX, and RY, right? That's at the heart of the whole problem. Within a modal formula, you have a subformula with two free variables. So, and that's exactly what is disallowed in monodic fragments. Monodic formulas are those in which only one variable may occur free in the scope of any modality. Once you have a modal formula, inside it, you can have only one free. Such a thing is called monodic. And they show that if we consider most well-behaved decidable fragments of first order logic, their monodic lifting to FOML is decidable. It's a very, very nice result. It shows that all that work we did for decidable fragments of first order logic, or many of them, you can actually lift it to first order modal logic, as long as you ensure that within the scope of a modal formula, you have only one free variable. And monodic formulas look suspiciously like one variable formulas, but they are not. They're more explicit. Now, the Barkan formula, for instance, it's in the one variable fragment. It's also contained in the monodic fragment. But if you consider a formula like this, it says there is an accessible world where Px holds, and there exists Y such that Qxy. This is monodic because this only exists occurring free, right? This formula uses two variables, right? It's not a one variable formula, but the latter is bound and only one variable is free. Therefore, it's monodic. So monodic formulas are more complicated. For instance, this is a monodic sentence in the sense there are no free variables, right? And because there is no modal formula at all. So you can have full first order formulas in general, right? But you can't write it in the one variable fragment at all. So you do So, and a crucial idea, I'm really summarizing things here, and I can go into details. I have no slides. So when we work only with monodic formulas, the main idea is that the modal subformulas contain at most one free variable. So if you take a formula like diamond phi, right, phi has no, where phi has no modality, right? The modal depth is only one. So phi has modal depth 0. Now this is an FO formula with one free variable, right? Because we have ensured that. Now, what you do is, if you are restricting yourself anyway to the first order logic, which is from some decidable fragment, right? Say like two variable or some prefix class, some. Right? What they say is that, okay, for that you had some idea, right? For those in that particular decidable fragment, right? You could do some model construction. If it were satisfiable, you would build a finite model, bounded model with some property. So basically build a quasi-model for this formula with some witness for the free variable, right? Now this witness you have to guess, and that you look at some formulas. After all, you use the same way the decision procedure went. You build boundedly many such quasi-models and use disjoint domains for all of them, right? So you have different diamond formulas. You have many different domains that you will get from model construction that you get inducted. Now, what you can do, you can set up an argument by induction on modal depth, building the model level by level. So you have your formula with some arbitrary modal depth. Start with modal formulas with modal depth 0, build your models, and diamond of these, right, will get you one level up. And then you have next modal depth. Inductively, for all of these models are floating around and build them. Now, this is not how water pressure. Okay. But this is one good present. I mean, this is the kind of thing that Ananta and I have built up a little cottage industry of, and we can do some results. But basically, this kind of technique works very well for projects, where you know that the base logic is, you have a decision procedure, you can use it to build up for but the realized types need to be combined carefully. Like I said, it's an elementary model theoretic technique. It's not very difficult, but it's subtle. I mean, there is a lot of detail. For instance, I wanted to work through this formula, but I don't have time. But here is one formula that you can take up and try to see how you could take a model for this, take a model for this, and combine and build up, this model gluing argument using realized types as 0 types, 1 types, 2 types. That's a very nice exercise. The other suggestion was, if you look at the undecidability proof, the modality acts as an extra quantifier, right? And because what you're saying is, the binary relation QXY Kripke translates into diamond of PX and RY. And diamond, if you remember in the first order translation, is an existential formula. There is one free first order quantifier. Now, the idea of bundling modalities and quantifiers is to limit this capability. So you don't allow freely quantifiers and modalities. You have formulas in the form there exists X box alpha, and for all X box alpha, that dot should not be there. And this is already very expressive. You can start saying things like, there is an X in all futures, such that it's not the case that there is a Y in all futures, where I read it as, there is a king element. I think this is Ananta's. Yeah, there is a king element such that after any update, no element is sure to dominate. Right? I'm just using that one example. For all X diamond is the dual of their existing box. And you can say every element can be changed when you go to the next word in such a way that another can necessarily dominate. I could have written it in terms of less than. So it's quite expressive. And note that now this is, and this was actually originally developed by Yanjin Wang to study there exists X box, where box is a kind of epistemic operator, to say something like someone knows, right? Which you treat as a single modality. And he went on to unify many such modalities, know what and know why and know etc. in epistemic logic. And but then it turned out to be a very nice thing that now once we have bundled modalities, we can freely allow relations of arbitrarity and drop variable restrictions. And this there exists X box bundle. There are two bundles here. One is the there exists X box and the other is the for all X box. The dual of this is for all X diamond and the dual of this is there exists X diamond. Okay. So this is like a Barkan bundle of the kind that we saw earlier for all X box. And these are two different bundles and they behave very differently. In fact, what we could show is that the latter, if you take the for all box, it's undecidable for constant domain interpretations, even with only monadic vectors, very similar to the kind of quick key result. In fact, it's a Kripke coding with just some extra subtlety. Whereas, if you take only the there exists X box bundle, it's p-space complete. Again, it's like modal logic. It's exactly as hard as propositional modal logic for constant domains, even allowing arbitrary. Then comes this thing. In fact, interestingly, if you take both bundles, it's p-space complete over varying domains with arbitrary. So you don't have to put conditions on arities, number of variables, prefix classes, nothing at all. You can consider the full logic, but you are only working with these bundles. But you must allow varying domains, expanding domains. In fact, expanding domains is how it's done. So, just a little bit of idea. So, the idea is that you can build a Tableau procedure for when you have this varying domain, especially the expanding domain semantics. The idea is that you build a tree model, you start with an initial domain, and as you need witnesses, you keep expanding domains as you go down. That's the idea. Your domain gets inherited, and you keep expanding as you go. So you easily add new witnesses as you need. The complication is that you need to add witnesses for existential quantifiers and successor worlds, which are other kind of existential quantifiers, simultaneously. And then you have subformulas of the kind for all diamond hanging around, right? So, but this is because any decision on one affects the choice of the other. So this is not completely trivial, but it's not deep mathematics either. Right? What we can then show, and then what is interesting is that there exists X box bundle. If you had only that, it cannot distinguish between constant and replaceable semantics. So you can actually, right in the beginning, guess sufficiently many witnesses at one go and use them as well. But as I said, the details can really trip you up. There's a lot of caution needed, but it's amazing that it works out. Okay. Skip some things. Okay, I should say this. Yeah, it's a pity that I'm almost at the end of my time, but okay. I'll just quickly mention term modal logics. These were introduced by Fitting, Talman, and Voronkov in 2001. You have, there exists X alpha, and then you have box X alpha. What does this mean? This means that your modality, right? It's not that you have box 1 alpha, box 2 alpha to interpret that many in the Kripke structure. This is, well, this is the sentence that Hintika discusses at some length. There exists X for all Y. If X is a witness, then witness knows who killed me. In fact, I should have put Y out there. So, yeah. It's a Y there. Yeah. This thing is. Yeah. So what is interesting model theoretically is we have a logic with an unbounded vocabulary, right? The number of relation symbols can be infinite. Because in the syntax, so think of it as first order logic, right? Where you don't have R1, R2, R3, etc., but you're saying Rx, right? and I'm saying something like there exists X, Rx, Y, right? So we are used to model theory where in general the logic has unboundedly many relation symbols. But you will say typically when you start with the logic, you fix a vocabulary, finitely many constant symbols, finitely many relation symbols, finitely many relation symbols, use that. Now you can't do that. Right? These are models. Every model comes with, as many relations as needed. So the formulas can actually force several relations. So the model theory is actually quite interesting for term. Now, PML contains a force, so it's not surprising that it's undecidable. In fact, even the propositional fragment is undecidable. And Ananta spent a lot of time on this. And in fact, Ananta's thesis has a lot of work on showing that propositional term model logic is already as expressive as full term model logic. So you can code up all of these into just propositional logic. And in fact, this holds even for the two variable fragment. And so that's a fairly surprising thing to see. This translation of term model logic into first order logic, modal logic is also very simple. If you have diamond X alpha, I go into a unary predicate which says X exists. Remember, this existence is always a problem. And that's it. And in fact, this preserves monodicity. And the translation can be used for showing a lot of PML to be undecidable, but you can also show it for getting decidability. Because we know that certain fragments of a sort of monodic fragments are decidable. So term modal logic can be translated, monodic term modal logic gets translated into monadic first order modal logic, and therefore you get decidability. Interestingly, the two variable fragment of term modal logic is decidable. Now, the two variable fragment of first order modal logic is undecidable. And in fact, it's undecidable with no equality, no constants. And so therefore, and that's not monodic either because it's two variable. So this is something new. And this again proceeds by constructing a tree model from root to leaf by induction on modal depth. What you do is very interesting is that at each level, the two variable model construction of Scott and Mortimer and Otto and Gradle that I was talking about, that is the kind of construction that you do locally at each level and you build it up. So you have a whole lot of those for2 models and glue them together into tree constructions. But that's why tree model properties are very important in this kind of style of work. So, and you have an analog of Scott normal form. It's complicated. And again, the use of realized types in this kind of model glue is tricky, but it works out easily. Okay, so I must conclude now. So I skipped many things, and many decidable fragments are known by now. The guarded fragment of term modal logic was shown to be propositional term modal logic was shown to be decidable by Orlandelli and Corsi. Staxer extended this to set quantification. Very nice results on bisimulation, characterizing bisimulation invariants and getting complete logics for these Van Bentham type theorems. So there are several things that are there. Many questions remain, like I mentioned right in the beginning. Equality is intriguing. And for instance, the two variable logic, which I said is decidable, add constants and it becomes undecidable. Add equality, we don't know. I think, on Tuesdays and Thursdays, we think it's decidable, and on Mondays and Wednesdays, it's undecidable. Yeah. Model classes, almost everything is open, right? Whole lot of negative results exist, but there's a lot, correspondence theory. First of all, in modal logic, one of the beautiful things is correspondence theory. For instance, there are modal characterizations of transitivity, right? And then you can show that on dense frames, at the level of frames, there's a lot of very nice correspondence. What is the correspondence theory of these fragments of first order? It's wide open. And expressiveness of, I said about decidability mainly, but what is the relative expressiveness of these logics? Like I said, even with one variable and monodic, it's sufficiently subtle. Right? Because the coding can be very complicated. And with two variable logics, it's much worse. So almost everything is open on this. Okay, stop. Thank you. Sorry, I overshot.
Thank you, Jam, for such a lucid talk. It's really, really wonderful. And is there any question from the audience?
I have a question. This is
Yeah,
Prabhat here.
yeah.
So the first thing, so modal logic is like used in, so there are lots of ways to interpret it. There is epistemic logic, for example, or even
Yeah.
other logics. So is there nice interpretations for first order modal logic also there? I mean, are there?
Oh yes, of course. I mean, first order epistemic logics, right? That's something that I am particularly very much interested in. And the whole lot of this was to actually work on first order epistemic logics. But and also, game logics, games where you have arbitrary number of players. So they're all some kind of first order modal logics. So that's, and then temporal logics. First order temporal logics, there's a lot of work. And again, whether you call it linear time, branching time. Yeah, so if you can live with the messy semantics and the need to carefully plan it, yeah. Only thing is that almost all these that you try out are in general undecidable. I mean, if you don't care for decidability, yeah, I would say.
So for example, PDL seems to be very nice object for like very nice extension to modal logic. But
Which one?
The propositional dynamic logic, PDL.
Yeah, PDL. Yeah, yes, it is. Yeah.
So if it,
but PDL is not first order. Huh?
No,
PDL is not first order.
First order. That's true. But if we try to like somehow hybrid it with first order logic, how would it look like? I mean, are there?
Oh, but that is what I mean. But that's why I said it's not first order. So you have to look at some kind of second order logics there, right? So, yeah. So that's, and I'm not touching second order at all. I didn't even talk about monadic second order. I'm only talking about first order. And as far as today's thing was that at least first order logic, there are decidable fragments. No, what can you do? Of course, there's a lot known about monadic second order logics. And you can ask, what about monadic second order modal logics? Like I said, guarded fragments, Staxer has something. But I must say, nothing nice. And then, yeah, I mean, you are talking about dynamic logic, which has transitive closure, right? But even transitivity is not clear, right? With transitive closure, I assure you, you have 5-minute undecidability. That's all. You get very easy undecidability. That's all. What is really tricky is trying to find, allow for transitive closure but retain decidability. That's really a challenge.
Any more question?
I have one.
Yes.
So is there any categorical semantics for first order modal logic?
There is one. I don't remember now.
Okay.
From New York. Alessandra's, I've forgotten her. Okay. She was doing her thesis on categorical punctorial semantics of modalities.
Okay.
So you think, I mean, roughly the idea is that you have all these objects sitting in each word, and then the modality you think of as a functor. And so there is a functorial semantics of first order.
Okay. Right.
Yeah. Alessandra Carvera. Yeah.
Okay.
She worked on that. But that's only one that I know of. I think there's probably a lot more, but I don't know.
Okay. Okay. Thanks.
But it just says that you can give such categories.
Yeah.
And of course, also the algebraic reading, right? Propositional modal logics are Boolean algebras with operators. And first order modal logic, Nova is not here. And topological Boolean algebras.
Yeah.
First order modal logics, I think these things are lifted very nicely. So stone spaces, some very nice results on this. So as I said, it's just that what is a natural, I mean, like things happen in a very natural way in modal logics. Nothing happens naturally. It's extremely messy. It's not.
Right.
These are not beautiful constructions. These are messy
Right.
ones. So finding the elegant classes is there the mathematical challenge.
Right. Thanks.
I guess that Guram Bezanishvili, their group is doing some work on these kind of things, like duality theory together with some connection with modal logic. And I don't know properly, but I guess that I read something about it.
I know that something is going on.
Yeah.
I know that they know.
Any more question? Okay. If not, then thanks again, Jam. We are really thankful for your encouragement, seriously. We are really
Thank you very much.
appreciate
It's a
it.
pleasure. It's my pleasure. Thank you. Thank you all.
Thanks a lot.
Bye.
Bye.